So just to present you the agenda quickly, we are first going to do a very light introduction to graphs to be sure that we are all aligned with the same definitions. Then we're going to understand what does it mean to do graphs at Windward, what is a Windward graph. We'll see how we developed our graph modeling here at Windward. And finally, we will see the 3 levels of graph study. So regarding graphs, very light introduction. It all started in a town called Königsberg. You've all heard about that probably. So it's a town that is divided in 4 parts, okay, and it has 7 bridges. One day there woke up and said, okay, could I cross all the bridges but to crossing each bridge only once? So I tried to answer these questions. I tried a few paths. It didn't work. And the thing is, you shouldn't try too hard. Euler proved 300 years ago that it's impossible to do it. He proved it using graphs. Okay, so he modeled his town by 4 entities who have links between them. And now graphs are basically everywhere. Okay, so just to illustrate this picture here, it's the World Wide Web, and you see all these web pages who have linked within each other. So you have this Facebook page linking to a Twitter page, linked to a Google page, and so on and so on. Let's give some quick definition here. Okay, so a graph, it's a collection of nodes and relationships or edge relations between them. Let's give an example. Okay, so this is a node, this is a person node, it has attributes. So it has a name, so this node is me. And you have another node, okay? It's a company node, it also has its attributes. And now we can create relationship between these two, okay? So here we have a clear relationship between me and Windward. Hannah is working at Windward as a data scientist, okay? It's important here to note that there's a direction between that node. Windward is not working at me, I'm working at Windward. And you can have a direction, or you could also not have a direction if it doesn't matter for this specific relation. Okay, so now we know what is a graph. Let's see what does it mean to work on a Windward graph, okay? First of all, why would we need Windward graphs? The maritime world, it's very fragmented, okay? Everything is complicated because people want to hide their identities, for example. And so this is a ship, but let's pretend for a second that this is not a ship, but that this is your car, okay? So you are the owner of your car, right? The car is yours, the same way the ship has its owner. What happens is that you are what we call the operator of your car, right? You are the one deciding if tonight your car will drive home, or if it will drive to the restaurant, or if it will drive to the cinema, okay? For a ship, it's another person who will decide what the ship will do and when it will do it. Then you're also what we call the technical manager of your car, right? You are the person taking your car for a repair, to fix a piece or whatever. For a ship, it's another person doing it. And it goes on and on and on for 7 levels of ownership. And this world is really perfect to hide yourself. So I'm going to show you a real-life example of such a ship hiding itself. So we see here a ship. It's sailing under the flag of Tanzania. Until here, nothing very weird. You look at it and you see that it was operating in the Gulf here, in Yemen here, and also in North Korea. And you're like, okay, why would a Tanzanian ship sail in North Korea? That seems very weird. When you look at this vessel, you see that it belongs to a Greek company. Once again, why? I don't know. A Greek company has no reason to send its ship to North Korea, right? When you look at this Greek company, you see that her parent company is a Syrian company. Okay, now you understand why this vessel was a bit weird in the first place. You see that this company, it's sharing its address, its exact same address and exact same phone number with another Greek company called massed shipping. Okay. And then when you look at this massed shipping, you see that it receives vessels from a company called Maziad Shipping. Basically, it's like I built a fake company called Khano, and Khano is selling vessels to me. Like, that's very weird for us, and especially that this company is sharing its address with the initial company. So we see here how we can close the loop and how these weird networks enable them to hide themselves, and how it's necessary for us to use networks. So this world, it was really necessary for us also because it's comprised of a lot of entities. Okay, so here we're talking, just so that we understand, of 150k ships. Okay, that's just part of the world fleet, and 60k companies. More than being a data motivation, there's a strong business motivation for us to be working with graph. So as Yael said, we're working a lot with intelligence agencies, and network analysis is a key methodology in intelligence gathering. And we're working, for example, with customers such as the DEA, the Drug Enforcement Administration. For those of you who saw Narcos and Breaking Bad, like, these are the police officers in these TV shows. And they are working a lot with network analysis, with tools such as Palantir and I2, if you're familiar with it, because their goal is to be able to understand the relations between different players in the maritime domain. And it was very important for us to be able to see beyond ships. Now we know, you know that we want to work with vessels, but you need to start somewhere, right? So basically, to start somewhere, you need to decide on your data modeling. That means to decide which nodes and relationships you want to include in your graph. As I mentioned earlier, we at Windward really work hard on combining domain knowledge and data science skills. So it was very important for us that throughout all the process, we validated all our models and all our approaches with business people. So on the one hand, we validated everything with our team of domain experts, our team of analysts here, and two, we validated everything also with our customers. And I think that until now you're pretty convinced, but if you're not, let me show you just one last time why you should use a graph DB. Because basically using graph DBs makes it much easier to find very complicated answers. Okay, so let's forget about maritime for a second, and let's take some kind of social network database. Let's say I want to have all the friends of someone who liked a picture of someone else who also liked a picture of another guy. This query seems it's not at all adapted to regular database. Okay, if you want to get your answer, first of all, you will need to query into a lot of different tables, and it will take you a few hours to write your query with multiple joins, and that's not something you want to do. You're not even sure that you will get your result in a sufficient amount of time. So here with the graph DBs, you can have everything within one single query. And second, graph DBs give you visualization tools. Okay, it's much easier to show a graph DB to a non-technical person than to show them a huge metric that is very hard to understand. So let me show you now the modeling that we've been doing and how complex and hard to grasp this world is. So let's say here that we have two companies in a ship, okay? We say that A is what we call the beneficial owner of the vessel, and B is its registered owner. Then we say that A is what we call the parent of B. Now let's copy this situation and paste it with another company. The same way, we have that A is a parent of C, right? In a family, when you have two children sharing the same parents, we say that they are brothers and sisters, right? So these two companies are sisters as well. Now we can make it even more complicated, okay? Let's add another ship here related to our two companies, and now what do we have? We have that these two companies are sharing vessels. Okay, but to have relations within company is not enough, right? We also need to have relations within your ships. And you have, for example, here, what I talked about, you have a relation between ship 1 and ship 3 of meeting. What does it mean for two vessels to meet? They might meet to exchange goods. Okay, so if you are a fishing vessel, for example, you will have your fish on your boat and you want to put it on another boat that has a huge fridge on it, for example. Or with your car, if we go back to this example, you will go to the gas station to refuel your car. A ship will go to another special type of ship for refueling. That's a vessel meeting. You also have other type of relation that we build at Windward. For example, what we call here similarity relation. If we think that two vessels behave the same way, then we created a connection between them to be able to identify them. So in the end, if you think about it, it makes about 100 million of connections in our graph. In order to play with this data, we needed to have a research tool to be able to investigate it. We went to the industry reference in terms of research. So it's a tool called Neo4j. It's a GraphDB. It has a lot of pros. Okay, so it's very easy to insert data in it. The query language is quite intuitive. It's called Cypher. It's very similar to SQL. It comes with an amazing visualization tool and with an out-of-the-box algorithm package, which was very convenient to use. It also has some disadvantages. The community version is a bit limited, so if you need very, very high performance, I suggest that you would turn to other tools such as Neptune from AWS or Titan, for example. So we managed to build a prototype of the Windward graph. So just so that you understand how it's working, you have here a console where you just put some queries, and here you have the result of your graph. So you have all these nodes, so all the blue nodes are companies. When it's circled with red, it's vessels, and you can just walk in the graph. So here I'm just showing the relations of this one, and then I want to open the relations of that other company by just clicking on it. So it's pretty interesting for us to be able to play with it. And I just want to say all our analysts are working with it on a daily basis, and they produce results, reports for our customers using this tool. So it's a pretty cool achievement for us here in R&D. Now, let's look at what is Windward graph modeling. Okay, we have one graph, but maybe we don't want only one graph. Maybe we want multiple graphs. Basically, there are two approaches to working with graphs. You can or put all your data into one huge graph, or you can decide to have multiple graphs, each graph for each problem. That's the approach we chose because it seemed easier for us to work with algorithms on smaller graphs. But that also had a disadvantage, right? Because we needed to be able to build a lot of graphs in a minimum amount of time because we wanted to try multiple experiments and to have quick iterations. So we built an internal library that is used to generate all these graphs. It basically works like Legos. Okay, you just build some pieces and then you just put all the pieces together and you choose which pieces you want for which problem, and then it enables you pretty easily to end up with your graph. In the end, you can build any graph in less than 10 minutes with all this work, without writing a single line of code. So it's pretty cool for us to be able to jump from one problem to the other, from one graph to the other pretty easily. This library we made it 100% compatible with Network X, which is the Python reference for working with graph. And it's also compatible with the Spark graph frame, which is Spark framework for working with very large graphs. So this is now how it looks like. You just have what we call a list of node builders. So here we have ships, ports, and then you have a list of what we call edge builders. So you have meetings, for example, Similarity that I mentioned also, and then within this line you can just do build graph and you end up with your graph in 10 minutes. Very convenient to work with in a data science team where you need to be iterating pretty quickly your work. We pretty soon understood that having a graph was not enough. You also need to play with it. So that's what we started to do. But we saw a few obstacles. Okay, so one of them was that our graph was a bit too big for some algorithms, and second, many algorithms did not support what we call multigraphs. So here you have two nodes, A and B, and many algorithms did not support the fact that between A and B you have two edges. So we had to find a way to be able to flatten it. So if we take this example, you have A, B, two relations, one that has a weight X, one that has a weight Y. I think that you see pretty intuitively how we can flatten it. So we created a unique relation that has a weight X plus Y. So this is a way of compressing your graph. It reduces the number of walks, making it easier to perform some algorithms in your graph. But on the other hand, you lose information, but that's what you're doing basically anytime you're averaging something or every time you perform aggregation, you lose information. We also been working on what we call reweighting our graph because it was very important for us. We pretty early realized that if a relation is very present in the graph, it will have a huge weight, right? Because it will be there a lot of times. But we understood that sometimes rare events are the most important, right? And I'm sure for you it's the same. The anomaly events are the most important, so it was very essential to us to be able to reweight our graph so that we tell the algorithm, please have a look specifically at these type of relations who are anomaly and are the most interesting. So the slide disappeared, it's fine. So now we're going to look at what we call the 3 levels of graph study. Okay, so I think there are 3 main levels of looking at graphs, working with graphs. So the first one is what we would call basic network analysis. It's to work on simple queries on your graph to be able to find insights. Second level is to perform more advanced algorithm on your graph, and the third level is to even fit your graph, to transform your graph to build features out of it. So now if we're at the first level, so we have one first level that is classic network analysis, so it's working with the kind of tool that we've been working on, the prototype I just showed you, to take insights out of it. So if you think about it, when you see a police movie in television, you will see they have like some kind of investigation board with pictures and gummies linking them. That's basically classic network analysis. That's the first level of working with graph. The second level is to ask, it's still in the first level, but it's to ask some query on it. It's a bit more advanced. So here, for example, we wanted to ask for each company to how many companies, other companies it was related to. Okay, so here on this graph, on the x-axis, you see the number of connections for each company, and on the y-axis, the number of companies. So pretty intuitively, we see that most companies are not connected to a lot of companies. Makes sense, right? This is what we call a small community world, and most communities are working that way. And so here, you see 5% of companies are connected to less than 8 other companies. Very intuitive. Here, what's interesting to look at is this long tail. Okay, this long tail, it seems weird for us. Like, why would a company be related to 50 other companies? That's very weird. And when you look at all these companies, you see that in the end, it's companies like China government, for example. So it's very important for us to confirm all our intuitions and to find the answers directly from the data and see that here, everything we thought we knew, made sense. It went here, This was the cool Breaking Bad study with the DA investigation board. You see, like, here, for those who know, you see the chicken place, and here the washing place. There's one very important, there's one key concept when you're working with graph. It's the concept of communities, right? It's kind of the equivalent when you're looking at a classic metrics. It's the equivalent of clustering, right? To find groups and to find structures within a dataset is something very important. It's a key methodology. So let's say here we have this very simple graph, okay? I think you can all pretty easily see how many communities there will be in this graph. So we have 1, 2, and 3 communities here. So what's very cool to see with working with graph databases is that it comes with new kinds of algorithms. And what was really interesting for us when working with Neo4j is that it came with out-of-the-box packages. And there was like this connector that we used for you to use. It's like called NX Neo4j. It's basically a Neo4j API for Network X. So I advise you to work with these kind of libraries because it makes it pretty easy to get answers once you know what you want to find, of course. So here you see you just project on a small graph, you say on which relation you want to perform your algorithm, and then within 2 lines of code you can get your graph clustering, if we might say. So let's analyze the results that we got. Okay, so in this graph here, you have on the x-axis the proportion of communities, and on the right axis the proportion of companies. Okay, so we clearly see here on this figure that we have 2 main parts in our graph. So the first part is that 30% of communities represent 80% of companies. Okay, so this is what we recognize as huge maritime groups. Okay, huge conglomerates of companies who are all subsidiaries one of the other, sharing the same phone number, sharing the same address, sharing vessels, etc., etc. And then the second part, it's about all the small communities, okay, where you have half of communities are smaller than 2 companies. These results were not at all surprising for us, okay? And they are not specific to the maritime domain, and that's very important to understand. You could have the exact same graph if you were looking at website traffic, okay? So here you would have probably all the Google, Facebook, Twitter pages would all be together in some kind of huge communities, and here you would have all the small independent websites. Okay, so now you saw that by asking quite easy queries, quite simple queries to your graph, you can get very powerful insights on your domain. It was very important for us to be able to learn new things on these new entities that are companies that we didn't know how to work with at the beginning. There's something very interesting with graphs, something that is very intuitive. Okay? In a graph, similar objects are more likely to create a connection one to another. Okay? Let's think about it. Let's forget about maritime and let's think about you and your friends. If all of my friends play tennis, okay, there is a higher probability that I play tennis as well, right? So basically we decided to take this concept to the context of vessels to be able to do risk inference within our graph. So quick reminder here. What is the labeling that I'm going to talk about here? We looked at the probability that a vessel, labeling as vessels involved in drug smuggling, weapon trafficking, oil smuggling. So we have this example here, a vessel caught with hashish in Spain. Then we have here all our vessels, like I showed you, with the different colors for risky vessels and not risky vessels. And now we're going to show you the work that we've been doing on an algorithm called label propagation, how we use it to be able to infer the risk of a vessel from the graph. So label propagation is what we call it's part of semi-supervised learning. Okay, so it's trained upon a combination of labeled data. So you see here, A, B, C, D are labeled, and unlabeled data. So here, X and Y. Basically, how it's doing, it's propagating to each node the average labels of its neighbors. I will show in detail in a second how it's working. What is very interesting with this algorithm is that it requires minimum supervision. 10% of label data is usually enough. And for all of you here who are working with label data, you know that it's very expensive, okay? And two, you know that when you're labeling data, you're introducing human bias, and if you can avoid this bias, you prefer to do it. So let's see in detail how this algorithm is working. So you put on each label, you initialize its score with its label, okay, each node, for the labeled nodes. For the unlabeled nodes, you initialize them with some value. This value doesn't matter on how the algorithm performs, okay? So here I put 0.5 to better understand the calculation, but that's it. And then you're propagating for each node its neighbors. So let's take this node X, and you're imputing it the average of its neighbors. So here 1 plus 1 plus 0 plus 0.5. You get 0.625. And then you're doing the same for Y. Okay, you're imputing in the value of A, C, of X, C, and D. And you're just doing it over and over again until it propagates. We saw that it propagates pretty quickly, even on a huge graph. Something like 20 iterations was more than enough to get propagation, so to get convergence. So it was quite interesting to work with, because you can do a lot of iterations and get pretty quickly results. And so these are the results after a few iterations, and you can here from there pretty easily go from the labels from the scores to the labels, and vice versa. So as I said, it's pretty quick. It gives you a degree of certainty on the prediction. Okay, so if I come back here, I am more certain that node X is red than node Y, right? And 3 convergence is guaranteed. At Windward, we wanted to tweak a bit this algorithm and not just propagate the average label of your neighbors. We understood that some neighbors are more important than others. So we basically propagated the weighted average of your neighbors, weighting this propagation by the weight of your edges. So we based our research on this project. So what is the research that we've been doing, the experiment we've been doing? So we've been working on the risk, on the intelligence risk model, so the model that Jair showed you. And as label data, we took the risk score of the ships, of how likely they are to be involved in smuggling activities. And our methodology was to forget 90% of our labels and to try to predict on the 90% using the 10% remaining. And what we got was pretty amazing. We managed to get 79% correlation between the actual risk score of the ship and the prediction of the label propagation algorithm. So it was pretty amazing for us to manage to get such, to recover so much information with only 10% of our data. And just for you to know, here we're just playing with the technology, okay? So we took a very, very aggressive approach of forgetting 90% of the data. You could get even better result by forgetting only 70% of your data. We wanted to just explore how it's working and how we could push this algorithm to get cool results. And here is an example of a real case that we found with this algorithm, okay? So this is a screenshot of the Windward graph. Okay, so you have here all these vessels. In green you have companies. In red and orange, it's like in the system, you have our very high risky vessels and our risky vessels. And you see this vessel in the middle, it was not flagged as risky by our current classic gradient boosting algorithm, okay? And when you open all the vessels related to this one, you see a lot of red, okay? It's important for us to understand that the prior that we put in our risk model, that our prior is that the proportion of risky vessels in the world is 5%, okay? Here in this picture, you have 15% of red vessels in this neighborhood. So we immediately see that it's much more than the prior. So perhaps something is weird with her, okay? It's a legitimate question to ask. It was very interesting for us to look at these vessels, and you see that, okay, it's starting from the US, then it's going to Colombia. So for people who are domain experts, a trip to Colombia enough would be sufficient to think something is weird with this ship. But whatever, went to Mexico afterwards. And when you look at it, indeed, it was a vessel that was busted for carrying cocaine. And if we were to come back to the relations of this vessel, you would see that he was visiting the same places in a port, not just the same ports, but the same dock in a port as a lot of vessels who were indeed caught for drug smuggling. So probably here we have some docks where drug smugglers know people, have friends, and they can just give them some money to pass the drugs on board. That's probably what's happening here. We've seen how there are two levels to study graph, and we didn't see yet the third one. Okay, the third one is what we call graph embedding. I think it's the highest level of graph study. Basically, graph embedding enables you to take your graph to the next level, to extract features out of it, to build features from your graph. You can use it for a classic generic classifier. You can use it to be able to do anomaly detection. For recommendation system, also you use a lot of graph embeddings. So it was very important for us to also touch this subject. It's important here to see that the work on this problematic is still, we haven't finished it yet. We're still investigating this subject. So for just what does it mean to embed a graph? Basically, to embed a graph, it's to learn a representation in a lower dimension of this graph to be able. So it's basically you have your graph, and you want to go to a vector out of it. So if you think of your vector, you can think of it as like simply a feature for your models. So we chose to look at the node-to-vec approach as a first approach to be able to validate our methodology and to understand what it means to work with graph embeddings. We know that there are a lot of other approaches, deep learning approaches, for example, such as graph convolution networks. It's definitely in our backlog, but we didn't have the chance yet to work with these techniques. We decided to work with node-to-vec also because it's you can easily understand it. Okay, it's very intuitive. For those of you who are familiar with NLP, it's working exactly the same way as word-to-vec is working. And basically, from your graph, what you're doing is that you're basically generating you're randomly sampling walks in your graph, and these walks create a corpus if we are like in NLP. So just for us to understand how there's a strong resemblance between NLP and graphs, this is a dog, so this is the graph representation of a sentence, right? So if you think of it like that, you start with your graph, then you're just sampling random walks, And if you think of it, each walk, this is your corpus, okay? And each walk within your sample is a sentence, okay? And then you can just use a basic node-to-vec model to be able to embed the same way you would embed your sentences. Here you embed your random walks and hence your graph. Node-to-vec is very interesting because it implements a biased random walk that enables you to explore your graph in different ways and to embed your graph differently. Meaning, basically, the random walks depends on 4 main parameters, okay? One of them is the number of walks. If you think of your GenSim corpus, it's just the size, number of sentences that you would have in your corpus. Then the walk length. What does it mean? It's just how many words you would have in each sentence to perform your word embedding. And then it's based on 2 algorithms, P and Q. P is what we call the return parameter. It's the probability to go back to an immediately visited node, and Q is the probability to be able to explore further nodes, okay, undiscovered nodes. And that's very interesting because by playing with these 2 parameters, P and Q, you can explore your graph in a more BFS style or in a more DFS style, okay, so as we see here in this picture. And so you can capture complete different things in your graph. If you're looking more at BFS, you will capture community structures. And if you look at DFS, you will capture more structural roles within your graph. So very interesting that with the same graph, you can look at it in 2 different ways and get or the hubs or the communities, or it really depends on your use case. So we decided to take a very simple a use case to be able to validate our approach and see that it indeed made sense for us. Okay, so we took a graph that had all the vessels visit to ports, okay? And basically we computed this embedding, and in the end you get, for each port you get a vector, and we decided to look at similarity between them. So how did we do that? We computed cosine similarity between each vector, and then we took the k nearest neighbors with the cosine distance measure. So we looked at a few results to validate that our approach made sense. Okay, so here, these are the results with the port of Ashdod. Okay, so you see that the most similar ports to Ashdod are the port of Haifa, quite makes sense. And then you have a lot of Turkish ports, and for us at the beginning it was a bit weird to end up with Turkish ports similar to Haifa, but then when you look at it, you look at the results, you see here that you have, this is Ashdod and Haifa, you see that you have all these vessels who are visiting both, and you have the exact same pattern with Ashdod and this weird Turkish port. So indeed, here, proving us that our methodology was working and that we could continue working with this kind of methodology. Then we looked at another example, okay? The port of Tartus in Syria. If you remember the example I showed you earlier of the Greek company that her mother was a Syrian company sharing information with another Syrian company, all these Syrian companies were located in this town, Tartus in Syria. So for us at Windward, people who work a lot with vessels, for also intelligence people, this is like a very bad place, very known place, this Tartus port. And as similar ports, we got a Syrian port. Okay, makes sense. The same way we had Ashdod and Haifa, we have Tartus and Tinaki. But that was very, like, not so surprising for us who know the domain, but surprising for someone who doesn't quite understand the geopolitical relations between countries, that you had Iran coming back so many times. Okay, but not surprising at all for us. Let me show you just the path of this vessel. Okay, so it's a ship that's coming from Iran. Okay, and usually when vessels from Iran want to go to the Mediterranean, what do? They go to through the Suez Canal and then go in the Mediterranean, okay? Just like Yair said, an hour of a ship costs a lot of money But here, this ship is doing this very weird maneuver. Okay, it's going all the way through South Africa to enter the Mediterranean. And here we see that something weird happens to this vessel in Gibraltar. I don't know if you remember in the news, but in July, there was like one Iranian tanker who was arrested by the European Union because they wanted to deliver oil to Syria in spite of American sanctions on Syria. And so basically, this is the vessel being arrested in Gibraltar. And then what happened is that the Europeans told her, okay, please, we will let you go, but promise us that you won't deliver your oil to Syria. They say, yeah, sir, we promise we won't deliver to Syria. But then if you see here, what happened, it indeed continued its path, and it stopped transmitting offshore Syria, and it's still not transmitting since then. But what happened is that it stopped transmitting, but that's not enough. This vessel was spotted a few days later offshore Tartus in Syria. This is satellite imagery from this ship. So it was very interesting for us to connect our algorithm and our research to real-life cases. So we have some next steps. So we want to look at deep learning approaches for graph embeddings. And also all the graphs that I've been mentioning until now are screenshots of a certain date, okay, the graph as of this date. And we definitely want to look at what we call temporal graphs to be able to see how edges appear and disappear within your graph and how basically you can get value from this time feature. Just for this research on graph embeddings, I want to say thank you to Omid Rokni, who has been working on this subject. So all this research is his regarding embeddings. As a few takeaways, so if you remember, we have the 3 levels of graph study. I want you to remember then that the first level is more than enough to get very significant insights of your data. You don't need to do very complicated stuff to get very significant insights. That's really not true. If you start easily, you will already get a lot of powerful insights. If you have a problem that you don't think can fit to a graph database problem, try it anyway. It will, just looking at your data through a graph to do some exploratory data analysis through the lens of a graph will provide you a lot of knowledge and very cool new insight on your data. And also take the time to create your infrastructure for quick experimentation. It will save you a lot of time later. Thank you. Ken, if there are some questions. So what is the difference between label propagation and PageRank? So these 2 algorithms are doing different things. Basically, PageRank, what it's doing, it's looking at the we had a whole research on PageRank that I didn't have to show. I can show it to you later if you want. PageRank, it's taken from, it's like the prototype of Google's search engine. And basically how it's working, it's iteratively counting the quality and quantity of links pointing to a certain page, okay? So it's basically identifying who are the hubs within your graph. Label propagation is something different. It's propagating your risk to others. So there's a research that we've been doing on trying to kind of hack PageRank for our risk purposes. It's what we call personalized PageRank. It's mostly used for recommendation systems. So it's not only to see who is important in my graph. Basically, that's what Google is doing. It's looking at all the pages, see who is important in my Google graph. There's personalized PageRank. You basically, your random walks are biased towards a seed. So basically, you're not just looking at who is important in the graph, you're looking at who is important in the graph for my seed. So our intuition was to do risk inference using this personalized PageRank to say that, okay, if you are very important to a bad guy, then probably you are a bad guy as well. So we have some outputs on this if you would like to see some of our results. But basically, it was just outputting you the biggest nodes in the graph, and that's not exactly what we needed to get. What was your trigger to be working with graphs? So, few stuff. First of all, our customers have been working with graphs for a long time. So we've been working the word network analysis, graph databases for a very long time, and it was very important for us to be able to reproduce our customers' workflow to be able to produce value out of it. And also it made sense, like we are all the time talking about two ships who are meeting. So our data is intrinsically talking about relations. So it was just for us another way to look at it. Yes?
So your graph is multiple node types and multiple different node types as well.
Okay, so the question is that we have a graph that has multiple node types and multiple edge types, and if we used a graph only with ships, for example, for label propagation or a graph embedding. So for the graph embedding, we took ships and ports to be able to create similarity between ports using ships. So we used both, but with a single type of relation, I think, Omid, that was just busy. Ship-to-ship relation also, okay. And for the label propagation research, that's a very interesting question because we have been developing here last year a model to be able to risk companies. And when we worked with label propagation, we totally thought of some kind of hacking that we could basically continue this label propagation to be able to assess the risk of a company based on the ship relations. So definitely that was one of the conclusions of our research. Yes. So the question is that we looked at node embedding, basically. Why didn't we look at edge embedding? So that's a very interesting question. We didn't have time to do everything yet, but this is indeed a very interesting idea. If we could embed a meeting relationship, for example, between two vessels, that could be very interesting. And we have a whole backlog on how to do a community embedding, on how to do an edge embedding. So these are definitely the stuff that we want to look at. Other questions? Yes.
What are the pros and cons of keeping the one big graph versus the multiple smaller graphs?
So multiple smaller graphs, first of all, when we were putting it into our visualization tool for analysts, it was much easier for them to work on a small graph. If you work on a huge graph, it explodes very easily, pretty hard to work with it. Second, when I talked about label propagation that took 10 iterations, 20 iterations to converge, it meant that every time I was running the algorithm, I could get results in less than 15 minutes. Okay, it means that I just go have a coffee, I come back, and it's ready. If I have an entire graph with 100 million of connections, you imagine how each iteration would take me so much longer. And for us at data scientists, it's very important, I think, to be able to iterate very quickly and to reproduce your experiments, because you don't always know that what you're going to do is going to work. So you want to be able to correct every time what you're doing and to do everything pretty fast. So that was the main motivation.